Hey guys, today we're going to be talking about waves. Specifically, Adam, I'm filming. As I was saying before, we're going to be talking about how longitudinal waves react. Today, we're going to be using slinkies. We will be using this slinky machine to help us see the amplitude, frequency, and wavelength of the longitudinal wave we are creating.
Like there becomes
Okay, I'm going.
oscillations, become more blinded.
Wow, that was really neat. Let's see it again.
We can now see this in slow motion. For this experiment, Wyeth pulled the slinky back 2 meters and started making waves. He attached the slinky to a fixed end, causing the waves to actually come back at us. Think of each coil as a particle passing along energy to the next. The slinky is the medium and the wave is the actual energy transfer through the slinky. We know how long it takes for one wave to move a whole wavelength, which is known as a period. By measuring the normal motion video, Wyeth found that it takes 5 seconds for the 10 waves to move through the system, meaning that the period is a half a second for a wave to move a whole wavelength. By taking the inverse of the period, we find the wave frequency. Frequency is measured in hertz, which is equal to 1/seconds. We can measure the wavelength by freezing the video and measuring the distance between 2 compressions. The compression demonstrates the peak of a wave. By using the scale of 2 meters, we can find that the wavelength is equal to 1.8 meters. If we multiply the frequency by the wavelength, which is measured in meters, we get meters per second. Now we know the wave speed. Frequency and wavelength are inversely related. If the tension of the slinky stays the same and we decrease the frequency, the wavelength gets bigger and vice versa. I can also increase the amplitude by pushing harder, but it is important to note that amplitude and frequency are totally independent of each other. Wave amplitude can be measured by how close the springs get together. The closer together, the larger the amplitude.
Good.
That wasn't bad.
Yeah. We can see on this graph a demonstration of a longitudinal wave as drawn as a transverse wave. The peaks are when the springs are closest together, and the valleys are when they're far apart. As we can see, the wavelength is 1.8 meters. Is it rolling?
It is.
Oh, okay. So for more information about this, we'll talk to Paul, the science genius.
So physics.
How does it work?
I don't know, you tell me. How does it work, Wyeth?
So, slinkies, if you put energy, it goes back.
It does.
It goes.
Why? Explain it, Wyeth. This is your project.
Physics! Now, let's talk about other longitudinal waves. We can see the same type of longitudinal wave as in sound. Sound is all around us. Sound is this piano. That's a C. Sound are these 2 jugs coming together. Sound comes up out of our mouths. Ryan, say something. That's sound. And music is sound. Sound waves are particles pushing themselves together and then moving apart. This image shows a visual representation of a sound wave. Each dot represents an air particle. We can think of sound waves a lot like the waves in the slinky. Think of each coil as a group of particles. The air particles get really compressed and then spread out, just like how slinky's coils get really compressed and then spread out. This is a transverse wave, where the force is opposite to the direction of the wave. Thanks, ladies. This is the first time I've ever talking to a girl.
Good. Yay.